Hi, my name is Mark Rychnovsky, and I'm going to present a recent work with Guillaume Barakant on the fluctuations for the extremal particle in a collection of sticky Brownian motions. So the plan for this talk is first, I'm going to introduce sticky Brownian motions and give a little background. Then I'm going to present the main theorem, which tells us the fluctuations for the extremal particle in a family of sticky Brownian motions. And finally, I'm going to talk about why we care. So what is sticky Brownian motion model? What are some connections to other models? So first off, to give you a sense of where sticky Brownian motion lives, here's a simulation of sticky Brownian motion. This model was introduced by Feller in the 50s, and he was studying continuous Markov processes on the non-negative reals, which behave as Brownian motion away from zero. He showed that this means that sort of only the behavior at zero is up for discussion, and he showed that the behavior at zero is always a combination of killing, where when your Brownian motion hits zero, it's moved to a coffin state and you just lose probability, reflecting, where when your Brownian motion hits zero, it bounces off, and absorbing, where when your Brownian motion hits zero, it stays at zero forever after. And so sticky Brownian motion is the boundary condition that interpolates between absorbing Brownian motion and reflecting Brownian motion. It's sometimes also called delayed reflection because it can be seen as taking a reflecting Brownian motion and slowing down time when your Brownian motion is at the point zero. This is not how we're going to define it today. We're going to define it in terms of a discrete model. So let's fix a positive parameter lambda forever and define a discrete random walk, z epsilon of t. We'll eventually send epsilon to zero. It'll be a walk on the non-negative integers. So this random walk is a symmetric random walk away from zero. And at the point zero, it jumps upward to 1 with probability epsilon times lambda, and it stays at zero otherwise. Now we're going to take a diffusive limit where we scale space by epsilon and time by epsilon to the -2. And note that this epsilon is the same as the epsilon which determines the rate at which we jump away from zero. So the model is being tuned as we take this limit. And we'll send epsilon to zero. The limiting process y is a sticky Brownian motion. It's not hard to see that this behaves as a Brownian motion away from zero. And if we want to understand the behavior at zero, we should think in terms of a law of large numbers. We have sort of in a interval of time, we have epsilon to the -2 chances to jump. The jumps are height epsilon, and at each opportunity, we choose to jump with probability epsilon times lambda. And so law of large numbers tells us that this just means we have slope lambda if we're exactly at the point zero. And so we behave as a Brownian motion when we're away from zero. And when we're at the point zero, we just have slope lambda, and sort of we have no diffusion piece. And colloquially, we will say that y of t leaves zero at rate lambda. So in understanding this, it's sort of important to point out that the set of times at which this sticky Brownian motion is actually equal to zero is positive measure with positive probability. And it's also nowhere dense. So there's no interval of time which is contained in this set. And you should think of this as being sort of like a fat Cantor set, the times where the Brownian motion's at zero. That was the one particle sticky Brownian motion. Now we want to talk about n particles, which behave as Brownian motions and stick to each other. So each particle will marginally evolve as an independent Brownian motion. Marginally evolve as a Brownian motion. They're independent when they're separated. And the sticky interaction means that if I take the distance between two particles, the norm of the distance, this behaves as a sticky Brownian motion. And so colloquially, we'll say that when we have two particles in the same position, a stack of two particles, they separate at rate lambda. And now there's a lot more than two particles in the system, so we could have a stack of 5 particles. And I need to tell you what happens then. So if I have a stack of m particles, then they evolve according to the same diffusion while they're in the same location, but they have slightly different drift terms, and these drift terms cause them to separate at rate theta k m minus k into a stack of k particles on top and m minus k particles on the bottom. And so, if I have 3 particles, they're trying to separate into 2 and 1 and 1 and 2 all the time. And these rate parameters, theta k m minus k, are parameters of the model that I need to tell you so that the model is well defined. These n-particle sticky Brownian motions were developed by Howitt and Warren in 2009, and they serve as the scaling limit for random walks and random environments, as well as for several other interacting particle systems. So I said that these theta km minus k's are parameters of the model. In fact, they're not completely free. You can't choose them however you want. They have to satisfy certain relations. And these relations can be neatly packaged by saying that for some random variable x, the theta km minus k's are all expectations of this form for the same random variable x. And we're going to be interested in an exactly solvable model, so we're going to make a particular choice that gives us clean formulas, and that choice will be taking x to be a uniform random variable on the interval 0, 1. We'll call these uniform sticky Brownian motions. All right, so how does the extremal particle behave? On the left, we've drawn 50 IID Brownian motions. On the right, we've drawn 50 uniform sticky Brownian motions. Classical extremal value theory tells us that if we look at IID Brownian motions, we take the maximum of a large number of them at time t. And note that I'm making a slightly odd choice where I'm scaling the number of Brownian motions with t in this way. Alpha is some positive parameter. But just bear with me. If we take this maximum, it grows linearly in t plus a logarithmic correction. And then we have constant order Gumbel distributed fluctuations. And so classical extreme value theory, we get the Gumbel distribution. Our main theorem says that if we have uniform sticky Brownian motions and we take the same maximum where we're scaling the number of motions with t in this particular way, then this grows linearly in t, and we have order t to the 1/3 scale Tracy-Whittem fluctuations. This is a distribution from random matrix theory. And this t to the 1/3 scale Tracy-Whittem fluctuations is characteristic of being in the KPZ universality class. So this sort of motivates us to say that this model is in the KPZ universality class. And there's a technical restriction in the theorem, but I won't draw on it because it's a restriction in the proof, not in when the theorem should hold. Okay, so why do we care? So there's this universal object called the Brownian web. It corresponds to coalescing random walks. I'm not going to define it here, but I will tell you that sticky Brownian motions are independent random walks through a pair of Brownian webs, and that Brownian webs are the scaling limit for the voter model and for models in population genetics, and that they're also pairs of Brownian webs give the scaling limit for random walks in random environments. And so we can our result connects the Brownian web, which is one universal object, which is the limit of some objects we care about, to the KPZ universality class, which we have some heuristic information about. And this confirms a prediction of Sun, Churcher, and Schwartz from 2017. Another reason you might be interested in this result is that sticky Brownian motions lately have been used to model the evolution of particles in colloids by Miranda Safron-Holmes. And if you're thinking to yourself, why would particles evolve as sticky Brownian motions rather than Brownian motions? There's sort of two natural reasons. One is if the particles have a very small scale attractive interaction. So as a cartoon, imagine that you had hydrophobic particles evolving in water. When the particles get very close together, they'd rather be next to each other than water, so they tend to stick together just a little bit. And this will give you a sticky interaction. Another reason is, typically your diffusions are being driven by some random background. So like water particles are hitting all your medium-sized particles you actually care about. and these are pushing them around. This causes you to have a diffusion, causes you to behave like a Brownian motion. And now you imagine if two of your medium-sized particles are next to each other, then it's possible that the pushes they're experiencing from the environment are very correlated because the water is behaving sort of similarly just in that little tiny region. And if the pushes are in almost the same direction when they're next to each other, this will also give you a sticky interaction as you zoom out. So a natural question is, for a particular system, is it correctly modeled as IID Brownian motions or as sticky Brownian motions? You have some actual physical particles and some physical medium. How should I model this? And our result suggests an experiment you could perform, at least in theory. You could take a very thin tube, put a whole bunch of your medium-sized particles in at the left, and allow them to diffuse. And then record the first time at which any of your medium-sized particles leave the right end of the tube. So if you perform this experiment several times, you can get an estimate for the variance of this exit time. And then you can use the size of this variance to distinguish between IID and sticky Brownian motions. And note here, you don't need like an exact estimate or anything. A very rough estimate for the variance will suffice, because for IID Brownian motions, you expect the variance to be constant in time. And for sticky Brownian motions, the variance is growing polynomially in time. So a very rough estimate will suffice to tell you which of these regimes you're in. All right, thank you. Here are some relevant citations. And here is the link to the paper on arXiv.